Hey, John here. Let's have a look-see at an interrupt request generator module that I wrote for my Z80 Project Nouveau.
A big thanks to everybody supporting my channel, all the likers, subscribers, thank you very much, especially the VIP Patreons listed here. See the links in the description below this video on YouTube if you want to become a Patreon as well. I'd appreciate it. Thank you very much. Today I want to look at this interrupt request generator here. This I wrote specifically for the video display processor module that's in a project that I'm working on, but this is a pretty generic thing. So if you need an interrupt generator, this should suffice for just about anything, provided that you need a level sensitive interrupt output. Okay, so that's what this thing is doing. In other words, it's not a single pulse type interrupt generator. As is the case with just about any Verilog module, we've got a reset signal and a clock for the domain that this thing is running in. When the reset is true, I reset my interrupt output, my flag that I used to output the interrupt request out of the module, which is this port right there. There are two inputs. One of them is a single clock period tick signal. I call that a tick when it goes high on a rising edge of the local clock domain, stays there until the next rising edge in the same clock domain, and then it would go low. The same thing for this read signal. Now, these are perhaps misnamed for this interrupt generator. I could make it more generic by using different names, but a rose by any other name is still a rose, right? Okay, so the way this thing is going to work is I get a single tick signal, and this module will latch onto that single tick and output it continuously on the output port here, and it will stay true until there's a tick on this signal here. And the idea is that quite often is the case in a peripheral for a CPU that the peripheral will generate an interrupt until the CPU comes back and reads a status register of some kind, at which point the interrupt signal will be cleared. Okay, so this is basically the acknowledgement that the CPU have seen the interrupt. So that's when you want to take it away. All right, so how do you then do this? Well, it's a really simple state machine is what we've got. We only have this one single flip-flop in this design, and this signal here comes out of the combinational circuit down here. So the only thing we got to worry about is if we're being reset, we clear our interrupt request output bit, which is assigned down here to the output port. And if we're not in the middle of a reset operation, we simply take whatever the interrupt request signal is supposed to be out of the combo circuit here, which shows up as IRC next, and we output it to the IRQ reg flip-flop. Okay? Combinational circuit works like this. If we have a tick signal from the circuit that this thing represents, right? So this is really part of a peripheral. And whenever the peripheral wants to generate an interrupt back to the CPU, it'll assert a tick signal here. Let's assume that this is 0 for now, because in a normal operation, the CPU doesn't pull this per se. It could, but it doesn't. Normally, it wouldn't, I should say. And so therefore this would be 0. It's a concatenation. So what we've got are 4 cases. So, all right, we got 0001, 1011. I got all 4 of them enumerated right here. And the idea is, depending on the current values coming into this module, if the peripheral wants to assert an interrupt right now, it should leave the module with the interrupt request set true after the fact. And you can see down here, whenever IRC tick is 1, it'll say, no matter what, I want the next state of the output to be true. Whenever the module is not trying to assert an interrupt, we ask, well, what is the status of the read register here? Okay? Well, if the CPU is not reading it, and the module's not asking to generate a new one, then the situation is the next state of the interrupt output here, or what would become that interrupt output, right, should be whatever it is now. Just stay the way you are. If we have a situation where the module is not trying to generate an interrupt or assert an interrupt to begin now, but I am reading the status register, well, that's the one and only one time when I know that regardless of the current state, if the CPU asks to see the state and it's supposed to automatically reset the interrupt request, it better go to 0. Okay? So this is the only way you can ever shut off the interrupt output from this module. If somebody reads what would be a status bit in a register somewhere, right? Now, this doesn't have a status register, it doesn't have that sort of thing, which is why I mentioned this might not be the greatest name for this particular signal. This should have maybe been called ERC reset or something like that. But in a larger context, what this is represents is the fact that the CPU wants to check the status, after which the status should be reset to 0 regardless of whether it's currently true or not. Okay? Now down here you see this other situation where it's both in a situation where the local module wants to begin asserting an interrupt request, and the CPU is simultaneously asking what's the current state. Now this is what you're going to want ultimately, and we'll look at this in a waveform diagram in a minute. It should make a little more sense maybe if you don't see it now. This is the module that controls this module, right? The parent module wants to begin asserting an interrupt on the next clock. Simultaneously, the CPU is looking at the current status, after which it will ask to reset the, and I'll emphasize, current status. Okay? So what that means is we have one of two possibilities. The interrupt request output here in this reg here is currently true or it's currently false. This doesn't care. So if you think about it, if the ERC reg value that goes out of this module is currently false, and we have both of these things true at the same time, then what the CPU will see is a status that says there is no interrupt right now, and please reset it, which will accomplish nothing because it's already a 0. This here is already a 0, right? And at the same time, some circuitry that uses this generator says on the next clock signal, I want it to become true. So the CPU sees I'm not generating an interrupt because I'm not. And the circuit says I want to interrupt starting on the next clock. So the answer is this should be a 1. If you do both at the same time, this should be run. Now, you could also argue that what if it's already generating an interrupt? What if reg is already a 1 and the output's already a 1 and the CPU is already being interrupted? And you would argue, well, that's why I'm reading the status register, which is why this thing ticks, right? And maybe I should set it back to 0. I suggest not. What that means to me is that whatever entity creates and uses this module has already, I mean, it has to have already asserted this once in order for this to have become true in the past. And the CPU currently reading the status register here, arguably it's seeing the status of the interrupt that was asserted before now, even though the circuit wants to generate another interrupt or continue asserting the current, a new interrupt after this current clock cycle, at which point it should become 1 again, or simply stay 1. All right? So what that would happen, how that would work is that, if over the course of time there was an interrupt tick signal, and then later on the CPU read it. So that would then go true. At the same time, some other code or the other circuit wants to generate another interrupt. So you should get 2 in that case. And this is the latest possible point in time in that scenario where the CPU could read it and see the first interrupt status and then finish its processing, return from a handler, and then find that the interrupt signal is still true, go back in the handler and read it a second time and get the second one, all right? So there comes a point in time where that can't happen anymore, and this is the edge case, right? This is your corner case where you have 2 interrupts in a row, this thing ticks twice, and the CPU reads the first one as late as it possibly can before it loses it, and then comes back for more later on. All right, so that's the whole state machine there. Now I got a test bench for this. In this make file, you do this to make it go, which opens up the viewer here. And I got a couple of scenarios in here. You can look at the test bench file on your own. I'll leave that as a task for the viewer. I guess we'll go ahead and look at the stuff that's inside the module here. Oops, I closed it. Watch what key you press. All right, open this up. Open that up. Go in here. Give me all the things. Append them all. Move this over because the default is to not show you everything for no reason. And what we got are a bunch of scenarios here. So what do we got? We got the irk next, the irk reg, the tick, and the reset. So the reset is, one and done up here. And in the scenario of the test cases, it serves to reset the, basically it zeroes this out, as we saw in the code, which causes then this thing to be reset as well. And the combinational logic also will then cause this to go low based on the current state and the lack of any tick signals, right? Okay, so here we go. A little bit of time passes. What do we got? We have a single period read tick when there's nothing going on. So this is basically represents the CPU polling a would-be status register in order to take a look at this IRQ output bit if it wanted to do so. Well, when it's 0 and it's polling it, it should stay 0. Not a problem. If it's not doing anything, nothing changes. If it sits there, this is theoretically impossible that a CPU could poll the register on every single clock tick. So this is ludicrously fast in terms of the timing. So if this ever happened, we're fine. Okay, so this represents a CPU that can execute an entire instruction and I/O operation on every single edge, every single leading edge of the clock, which it's not going to be able to do that fast, okay? So speed test looks good, okay? So what do we got here? Do nothing in this cycle. Then we have, what's this guy? We have, that's IRQ next. Here's the reg. Here's the IRQ output. This is, okay, this is the ramifications of this thing. Let me put these up on top because I kind of think in terms of inputs on the top and the outputs on the bottom. This is the actual module output, which is equal to this at all times. So we can just delete this because this simply is that assign at the bottom of the module that says assign IRQ equals this. So this is just in order to route it out of the module port. Okay. We don't really need to see this either, but sometimes I like to have it up there. So we'll leave it on for now. So what's happening here? I got an IRQ tick. So the parent that created my interrupter says, I want to generate an interrupt starting on the following edge here. And that's what we see. This down here is the output. And the combo circuit reacts to the input right away in our state machine here, right? So that's why the next goes true as soon as it sees this edge here. Now remember that the case statement in the combo circuit uses as its inputs the what is it using? It's using the IRQ tick signal and the read tick signal to decide what to do next. And when neither of them are high, it's that first case where we simply say IRQ next equals the current IRQ reg, which is IRQ, right? So that's why the next stays 1 here. Here is the module being asked to assert another interrupt, 2 in a row. So this represents a case where the CPU missed this first one. Well, what should I do if I say interrupt and then I say interrupt a second time? Well, I don't really have an option. I simply keep the interrupt output signal true when the new one arrives, okay? Then later on, I have a scenario here where the read tick goes true. So this is the CPU saying, hey, I want to look and see what the situation is of the interrupt. And normally the wrapping module that would use this current module, the IRQ module, would send the value of the IRQ output bit back as the status during this read, okay? And after the read is completed, it should clear this IRQ output. Next clock period, we don't do anything, and the rule when you don't do anything is to leave the next equal to the current, which is 0, okay? We then read it again gratuitously. There's no interrupt being generated right now down here, therefore there's nothing really to do, after which point it makes sure that it stays 0, and that's that one case where you saw me assign a 0 to it in the combo circuit, right? So here's a scenario where we do both an IRQ and a read at the same time when the current interrupt status is a 0, as you can see down here. So when we do that, that was the last case when they're both asserted at once. What do? Well, in this scenario, the observer, if you can use this module however you want, and the way I'm going to use it is when you read, when the CPU wants to see the current status, I'm going to send out the value of the IRQ output at that time, which is 0. I'm going to say I'm not generating an interrupt. And at the same time, the circuitry involved with the source of the interrupt is also asserting that I want to start generating an interrupt on the next clock signal. Okay, so this is it reading and seeing there is no interrupt, followed immediately then by the interrupt becoming true because they're both 1 at the same time. You then see another CPU read here. Presumably you'd send the 1 back and say, hey, the interrupt is on right now. CPU says, okay, fine. And it's all happy because it sees an interrupt. And we see it get reset because it was read. We see a clock period where nothing happens at all. We see then down here a regular old interrupt that's asserted and generated on the next clock signal. And this time what happens is the CPU reads it, presumably while polling, because it doesn't currently see any interrupts out there. It just decides to read it. But coincidentally, we generated an interrupt at the exact same time. Okay, so right as I start reading, we asserted the interrupt, so it sees the 1. We have read it, and we sent the 1 back. So after that, it better go back to 0, and we see it does. So these test cases aren't too bad. We can see all these kind of corner timing cases, make sure that we don't accidentally keep it on in this scenario. Clearly it should go off. Make sure that it's on and stable during the read operation so they don't accidentally see a 0 and then we reset it, or it doesn't go high halfway through here and all this other stuff. Okay? Because one of the reasons I did all this and I'm trying to make this work correctly is because I'm modeling an actual integrated circuit from Texas Instruments from 40 years ago, where they did all this and these timings weren't kept correct. And I have a video on that. You can take a look at the playlist below in my Z80 Retro VDP card, where the CPU is polling the interrupts from that chip, and they decide to assert the interrupts right in the middle of a read. So you might get the 0 or you might get a 1 if it goes high in the middle of a clock period. Quite often what we saw was it might be asserted, like this scenario over here, when the read arrives, and then it becomes deasserted before the read is done. At which case you had an interrupt, and then you read it, and the read was supposed to reset it, and it did reset it, but it reset it so soon that the CPU saw a 0 and didn't notice that it was on. So that's garbage. You don't want it to work that way. So I really want to make sure mine won't work that way. So here's another scenario where it's running ludicrously fast, where we have multiple, again, this is all so fast, it's impossible, as is over here. These are it going back and forth repeatedly to make sure that my state machine doesn't get stuck on or stuck off or do something wonky. So again, these are all kinds of crazy corner cases. If it works fast, it'll work slow as well. So, I mean, and by that I mean if we wait 1 clock here or 1,000 clocks, we're fine either way. Over here, you'll notice it's generating interrupts one every leading edge of the clock. This is ludicrously fast interrupt generating and ludicrously fast resetting of the interrupts, okay? And if it works in there, and it works here, and it works like this, it'll work anytime, okay? So, all right, so we saw this one. What does this one do? Don't do anything, so it stays on. Then we have reading and asserting a new interrupt on the next clock cycle at the same time, and arguably it sees this as a 1 during the read. And we want to assert a new interrupt, so it stays asserted over here. During a period we do nothing, and it stays on. Then we're going to read and see that it's on and assert it so that the next cycle it remains on, and it does. Okay, during which time we're going to read and assert again. And we can see over here, it stays on. Then over here, we're going to read and see that it's on and reset it at the same time again. Okay, while asserting it. So it stays on after this leading edge. Now, at that point, the interrupting source decides I'm not going to generate anymore. But it did generate one on this rising edge here, which you see during this cycle here. Okay, and then you see the CPU polling, reading the status again, while we're not asserting a new interrupt at start, in this signal, or rather this time period over here. So it finally goes back to a 0 over there. And this is right. Correct me if I'm wrong. Comments below. Always welcome any constructive criticism on my channel. I always appreciate it. If I can learn something from this, great. Okay. All right, so what do we got over here? We generated an, okay, this is when it goes back and forth. I'm going to generate an interrupt in the next clock period, and you can see that right down here. And then I'm not going to generate it anymore. I'm going to do a 1 period where I'm wanting to tick and say I want to begin asserting an interrupt. And then in that very next time period, I'm going to do a read, right? So this is the read tick. CPU says, hey, what's the status? It sees, oh, it's a 1, at which point it says, okay, I want to reset the interrupt status. And you can see it goes to 0 in this period down here. And during that same period over right here, we want to assert an interrupt for the next period, which you can clearly see the interrupt goes back on. And again, we simultaneously try to read it by looking at the, like I said, the would-be status register that allows it to peek at the interrupt status. It would see a 1. And because we've read it, we want to reset it in the next clock period. We see it go back to 0. And what happens if you keep reading when it's 0? Well, it's 0, it stays 0. That's exactly what it should do. So these are a bunch of, test cases. If I missed one, let me know. I'll add it. But this is really what you want it to do. So I declare this a functioning module. That's my test case. And that's how it works. So we can now use this to generate interrupts and send them to a CPU in a level, sensitive interrupt input type of design, of which most micros back in the day worked that way. And by that I mean that the CPU itself wants the interrupt request signal to go on and stay on until it acknowledges it by reading a status register or polling it or acknowledging it in some way, which is what this thing represents, right? And that's in stark contrast to the CPU actually working like this module does, where the CPU, there are CPUs out there where you can give it a single tick and then take it away, and then the CPU remembers that there was a tick out there and it'll service an interrupt and stuff like that. But I can't name any off the top of my head, but I swear I've seen some that work that way, or it might be that I've seen interrupt generating modules that actually do what this is doing, that were chips that you could buy that take ticks and make them into level type outputs and things like that, that then could go to a CPU that is of the ilk that I'm familiar with, is Z80 and 8080, 8085, and all the stuff of that area, the 6502 and so on, because they want to have this continuously asserted interrupt signal that goes on and stays on until the CPU is prepared to react to and service the thing and acknowledge it, right? With something that this module will experience as the arrival of a single tick read signal. All right, so let me know what you think in the comments below. I really like it when people add to these things, so if I missed something, let me know. Thanks for watching. I'll see you next time.